We are going to begin by defining what modular construction actually means. Modular construction is an industrialized building method in which major portions of a facility are produced as separate modules in a controlled off-site factory. These modules are then transported to the project site, lifted into place by crane, and connected to a permanent foundation. The important point here is that modular construction is not simply building boxes in a factory. It is a planned construction delivery method that changes where much of the work takes place. Instead of completing most construction activities on a weather-exposed job site, many activities such as structural framing, MEP systems, interior finishes, flooring, and cabinetry can be completed in a factory before the modules arrive on site. This slide also highlights the role of DFMA, or Design for Manufacture and Assembly. In modular construction, the building must be designed with production, transportation, lifting, and installation in mind from the beginning. In other words, the project is engineered more like a product than a traditional field operation. Finally, it is important to distinguish modular construction from manufactured or mobile housing. The modular buildings we are discussing in this course are code-compliant, permanent real property. They are placed on permanent foundations and reviewed under applicable building codes. This slide introduces the major types of modular construction. The first type is volumetric modular construction, sometimes called 3D modular construction. In this approach, the factory produces fully enclosed room-sized units. These may include hotel rooms, dorm rooms, apartment units, bathrooms, or repeated patient rooms. Volumetric modular construction is highly efficient when the building has many repeated spaces. However, the module size is limited by transportation requirements, especially highway regulations and route restrictions. The second type is panelized construction, or 2D prefabrication. Instead of producing complete three-dimensional units, the factory produces flat components such as wall panels, floor cassettes, and roof assemblies. These panels are shipped flat and assembled on site. The third approach is a hybrid system. Many projects do not use only one method. For example, a hotel may use volumetric modules for repeated guest rooms, but conventional or panelized construction for the lobby, restaurant, or other open spaces. This allows the project team to use factory production where repetition is strong while still preserving flexibility where it is needed. The slide also shows the difference between permanent and relocatable modular buildings. Permanent modular buildings are attached to foundations and intended for long-term use. Relocatable units, by contrast, are designed to be moved and reused at different locations. Finally, modular construction can use different structural materials, including wood, cold-formed steel, structural steel, concrete, or composite systems. The best choice depends on building height, fire resistance, sound control, structural needs, cost, and local market conditions. This slide explains why owners and construction managers choose modular construction. The central idea is parallel work. In traditional construction, many activities happen sequentially. Site work comes first, then structure, then enclosure, then rough-ins, then finishes. Each stage often waits for the previous stage to finish. In modular construction, the sequence changes. While the site contractor is preparing the site and building the foundation, the factory can produce the modules at the same time. This overlap between factory production and site work is one of the main reasons modular construction can shorten the overall project schedule. As shown on the slide, modular construction is often associated with faster delivery, better schedule certainty, cost savings, improved quality control, fewer safety incidents, and reduced material waste. These benefits are connected to the controlled factory environment. Materials can be stored indoors, workstations can be organized more consistently, inspections can happen at planned checkpoints, and workers can repeat tasks in a more predictable production flow. However, these benefits are not automatic. Modular construction only performs well when the project is planned properly, the design is stable, the manufacturer is involved early, and transportation and installation constraints are understood before production begins. So the key message is this: modular construction is not faster simply because workers build faster. It is faster because the project is reorganized so that factory production and site work can move forward at the same time. This slide is very important because modular construction is not the right solution for every project. Modular construction is usually a strong fit when the project has a high degree of repeatability. Examples include student housing, hotels, apartments, military housing, and patient rooms. When many spaces are similar, the factory can repeat details, reduce learning time, improve consistency, and increase production efficiency. It is also a strong option when the project is schedule-driven. For example, a residence hall may need to open before the beginning of a semester, or a hotel may need to open before a tourist season. In these cases, earlier occupancy can create significant value for the owner. Modular construction can also be useful on constrained sites. Urban projects may have limited laydown space, delivery restrictions, and noise limitations. Remote projects may face labor shortages or short construction seasons. Moving more work into a factory can reduce some of these job site challenges, but the slide also shows when modular construction may be less suitable. Projects with highly unique layouts, very large open spans, irregular geometry, or frequent late design changes may not benefit as much from modular delivery. The most important warning is shown at the bottom of the slide. Late changes can affect every repeated module at the same time. That is why design freeze is critical. Once factory production begins, even a small change can become expensive if it must be repeated across dozens or hundreds of modules. This case study compares two residence halls built at Appalachian State University, Mountaineer Hall and Summit Hall. Mountaineer Hall used modular construction, while Summit Hall used conventional site-built construction. This comparison is useful because both projects were student housing projects, but they produced very different outcomes. Mountaineer Hall included 460 beds and approximately 118,434 square feet. It was completed in under 12 months and cost about $16.5 million, or roughly $36,000 per bed. The key advantage was that factory production and site work could happen in parallel. While the foundation and site work were being completed in North Carolina, the modules were being manufactured off-site. Summit Hall, by contrast, provided 333 beds, took nearly 2 years to complete, and cost about $31 million, or roughly $93,000 per bed. Its delivery followed a more traditional sequential construction process. The lesson is not that modular construction is always cheaper or always better. The lesson is that Mountaineer Hall was a strong candidate for modular delivery. It had a highly repetitive dormitory layout, a firm schedule need, and spaces that could be efficiently produced as volumetric modules. By choosing modular construction for the right project conditions, the university gained more beds, reduced cost per bed, and opened the facility sooner. The case also shows why early planning and project suitability are so important in modular construction.